We have many transformation, use of change of coordinates, particularly when we take derivative, we substitute coordinates. Suppose y is equal to something into x, not it? That type of transformation is not a point transformation. Point transformation means we are changing one coordinate, x to y or x to t, y to t. That is called point transformation. But when we want to change two coordinates, that particularly in case of phase space, we call that transformation is canonical transformation. So in point transformation, we change one coordinate. Let's say y is equal to 5x or y is equal to ax. We put in your derivative case. Similarly, here you can put capital Qj is equal to function of small qj and t. So y is a function of x here. That type of transformation is called point transformation. But in canonical transformation, we have to change one set of coordinates or one pair of coordinates to another. QP to new set, let's say capital Q, capital P, such that new one capital Q is a function of small qp t and capital P is also function of small qp t. This transformation is known as canonical. And one important thing is for canonical coordinates, its Poisson bracket is 1, and in quantum mechanics, their commutator is IH cross, and they only obey uncertainty principle. If the pair of variables are canonical, they only obey the uncertainty principle of quantum mechanics. Classically, we say the Poisson bracket of those pair of particles should be 1. Okay. So in canonical transformation are characterized by the property that they leave the form of Hamilton's equation of motion invariant. So canonical transformation actually means the transformation which leave the form of Hamilton's equation of motion invariant. Suppose here is capital Q is nu Q, capital P is nu P. So here we say there exists a Hamilton equation. Let's say S may be K, del K by del Pi is equal to capital Qi dot. Similarly, del K by del Qi is equal to minus capital Pi dot. Hamilton equation also exists in new coordinate in the same form. Okay, that is called canonical transformation. So Qi K is a new Hamiltonian, and Qi dot is equal del K by del Pi dot minus del K by del Qi. So now we can use the variational principle to get the function which obeys this type of transformation. The function k plays the role of Hamiltonian in new coordinate. Okay. We know that from Hamilton's principle, L dt is gives integration of L dt for exact path of motion is a constant, so its variation will be 0. But L is equal to summation of pj qj dot minus s, so its variation is 0. In new coordinate, small p is replaced by capital P, small q is capital Q, and h is k. So this variation is 0. Okay. So now this is 0, this is 0. If we add these two, we get also another new 0. So again, we can define a function delta of del a by del t dt t1 to t2 actually as 0. Let's say its derivative will be f. Del t by del cancel, df is f. Result is f. So we define a function f which vanishes at both t1 and t2, two endpoints of the motion. T1 suppose 1 point and 2 point, that function vanishes. If vanishes, its variation will be 0. You cancel the constant. If f is constant at here, then del f 0, constant 0. So at endpoints, variation vanishes. We take that function. So if this is our case, this f may be a function of all old qp, new qp, and time. We have to assume a function of old set of coordinate and new set of coordinate such that its variation at two endpoint is 0. So if it is 0 now, but we know df by dt, if f is a function of this, and df by dt is equal del f by del qj dx qj by dt, del f by del pj dpj by dt, del f by del capital qj del qj by del p, del F by del capital Pj dPj by dt, del F by del T into dt. Okay. So which is actually equal to, see, if we integrate with t respect to t, del F by del Qj remains same. This integration gives you delta Qj at T1, T2. Here similarly gives you delta Pj, delta Qj, delta Pj, del F by del T, that is equal to 0. So that you can say delta of which quantity? T1 to T2 integration Pj Qj dot minus k. This term is 0. Okay. Means this one is 0. We already know from equation 1 this is 0. Equation 2 this is 0. This is our assumption 0. We explain our assumption. It is not necessary actually for derivation. Here only explain our assumption. We have for old coordinate this is 0, new coordinate 0. We add a term because two are equal, 0 is 0, but exactly if you add a derivative of constant, it is also 0. So when you compare two things, we exactly don't write this, but we add some constant. Okay, that's the case. So now we add all three. 0 plus 0 plus 0 is equal to 0. We here add this Pj Qj, this term 0, so a constant lambda into this is also 0, plus df by dt is equal to 0. Isn't it? Can we add three zeros? If we add three zeros, it will be 0. It is 0. If I multiply lambda here, lambda into 0 is equal to 0. Okay, no problem. So from this equation, you can say it is arbitrary integration. This value 0 means this bracketed term must vanishes always. So Pj Qj dot minus k minus lambda Pj Qj dot plus dA by dt is 0. So lambda plays an important role. So if from this you can say lambda Pj Qj dot minus s is this. If lambda is equal to 1, we call it canonical transformation. For our case, lambda is equal to 1. If lambda is not equal to 1, we call extended canonical transformation. If you anywhere see some complicated problem, and then you can solve using this extended canonical transformation. But in our syllabus, only canonical transformation is given. For our case, lambda is equal to 1. So we have a relation like this. So this function f is known as generating function, and this generating function actually function of old coordinate and new coordinate and t. Okay. So df is equal to how much? If you compare here, df is equal to, you see, summed over pj qj dot minus capital Pj dqj dot. Now here pj qj dot means pj dqj by dt. Similarly here dqj by dt. Here df by dt. H and k Hamiltonians. Hamiltonian for a conservative system, Hamiltonian is nothing but total energy E, T plus V, which is a constant. For a conservative system, total energy is constant, you already know that. So K is also represent Hamiltonian in the new set. So that is also constant. So these all are constant. If you cancel the T dependence here or integrating that part, you can write summed over J Pj Qj dQj plus minus P capital Pj dQj is equal to df. So for a transformation to be canonical, this sum means the difference must be a exact differential. Exact differential means we can take its derivative of d of something. Okay, this is one of condition to check canonical transformation. But the easiest way is to check the Poisson bracket of capital Q, capital P as 1. Another way to check that this difference is the exact differential. This f is known as generating function, and it can be take one old coordinate and other new coordinate. So actually there are two old coordinates small q small p, two new coordinate capital Q capital P. F is a function of one old coordinate and one new coordinate. So it has four forms. One is small q, old q, new q. old Q, new P, old P, new Q, old P, new P. So there are four forms of generating functions, and from that generating functions we can get equations, four kind of equations of motion, F1, F2, and F2 is more general and it's common. So F2 generating function Qj, Pj is common one, because so if F1 we take Q, Qt, then differentiating it, you get this del F by del T. Comparing with summation of Pj Qj dot minus h, we can found set of equations. Small Pj is equal to del F by del Qj, capital Pj minus del F by del Qj. Similar, taking second function Qj Pj, small q capital P T. Okay, we get equations capital P del F2 by del Qj, cap sorry, small p del F2 by del Qj, capital Q del F by del capital Pj. Since here both are positive, it is common one. And in general, if we say about any generative function, we have to write this F2. F2, which is a function of small q, capital P, T. Or you can say small qj, capital Pj, T. And the equation of motion means it is given small q, capital P. We have to get small p and capital Q. How small p and capital Q we have to calculate it from this F2 by using this relation. For F2 case, both are positive. Pj is equal to del F2 by del Qj and capital Qj is equal to del F2 by del capital Pj. Always small are related to small and capital are related to capital. Similarly, for F3, which is a function of small p, capital Q, there is a relation exists. Small q minus F3, small capital P this. For 4 also a set of equation exists. Okay. This is one problem, how to calculate these things. Suppose a relation exists between small p q and find the generating function. Given capital Q q square, capital P p by 2q. We know, but here capital Q capital P. But we know one old, one new. Relation given, we can calculate it. For that reason, you see here, it is easy to define which one. Capital Q q square, small p is equal to 2q capital P. Okay. We know small p is equal to del F2 by del Q. So del F2 by del Q is equal to 2q capital P. Del F2 is equal to how much? Fq is equal to 2q p dq means q square p f of p. Again q is equal to q square. But we know q capital Q is equal to del F2 by del capital P. Using that formula, F2 is equal to capital Q dp integration q square dp integration which is q square p fq. So from both result we found it is q square p. So you can say function is here q square capital P. Okay. Some other problems are given here. You have to calculate Hamiltonian energy. Okay. These are the few problems. Poisson bracket is canonical invariant, which is our aim. You have to check when you have check a transfer of a canonical. We see the Poisson bracket of new variable is invariant. Okay. So these are the derivation. You have to remember this from problems. We use this formula. Again also, we have a Liouville's theorem. We will discuss in the next classes, so where it is required. Next thing is that Poisson bracket. What we are thinking? This is the Poisson bracket formula. We already written UV Poisson bracket del U by del Qj, del V by del Pj minus del U by del Pj by del V by del Pj. Properties of Poisson bracket, just like commutator of quantum mechanics. If you change position of UV, it will obviously minus sign because there is a minus exist. If you make U is equal to V and V is equal to U, obviously there is a minus sign. Okay, which implies if we both are same, it will be 0. So Poisson bracket of same quantity is 0. Again, U plus VW Poisson bracket is equal to UW plus VW. AU VV Poisson bracket is FV into UV Poisson bracket. AU plus VV W Poisson bracket is equal to A UW plus B VW. Okay. D by dt of UV is equal to del U by del T V plus U del V. That's the formula. Now fundamental Poisson bucket. If you take U is equal to Qj and it is Qk, we get 0. Same with 0, whether j is equal to k or not. Pj pk 0. But if you take qj pk, qp 1. So qj pk means delta jk. When j is equal to k, it is 1. Pj qk is minus delta. If alternative, vu is minus uv is equal to minus 1. Or simply one coordinate you write qq0, pp0, qp1, pq Poisson bracket minus 1. Okay. So a transformation is canonical if capital QP Poisson bracket is 1. Now time derivative we will discuss that du by dt is Poisson bracket of UH del U by del T. So time derivative of any quantity can be equal to Poisson bracket of that quantity with H. If actually that does not contain time explicitly. Del U by del T 0, then we have a relation constant of for constant of motion, its Poisson bracket with H must vanish. From that formula, you get QA dot H, QA dot H. These are some problem. If A, B are constant, and capital Q is A dot P, capital B is B dot R, then find the value of A dot B if the transformation is canonical. If canonical, it is Poisson bracket 1, A dot P, B dot R 1. So you take this Poisson bracket, P means 3 component, Px, Py, Pz. Dot product means Ax, Px plus Ay, Py plus Az, Pz. Vxx, Vy plus Bzz. Taking Poisson bracket, only Px exists non-zero, which is minus 1, Py minus 1, Pz minus 1. We got is minus. My A dot B is equal to minus 1. Okay. There is a Poisson's theorem. Poisson's theorem tells that Poisson bracket of any two constant of motion is also a constant of motion. If u v are constant of motion, then Poisson bracket of u v is also a constant of motion. And Jacobi identity, we said that Poisson bracket of three quantities taking in the order u v w plus v w u plus w u v is equal to 0. Okay, the identity. As angular momentum and Poisson bracket. If you see the angular momentum L is equal to R cross P, if we calculate the component, cross product calculated in terms of determinant, you found I cap y pz minus z py plus j cap z px minus x pz plus k cap y minus y px. This term is Lx, this is Ly and Lz. Okay. If you take Poisson bracket of Lx Ly, the formula using, we found it is nothing but Lz. Similarly, Ly Lx minus Lz if you change UV, Ly Lz Lx, Lx L order. If in order, then it will be plus XYZ, YZX. Okay. So the general formula is Li Lj epsilon Ijk Lk, which is Leibniz beta symbol. If it's 0, if two indices are same, plus 1 if even permutation and even order, clockwise order, minus 1 for odd permutation. Okay. So you can say commutator in quantum mechanics is IH cross into classical mechanics Poisson bracket. There are a few problems. A system is governed by this Hamiltonian. If A, B are constant and Px, Qy are moments conjugate to it, then find the value of AB. If these quantities are conserved, the constant means if derivative 0. We know if it's constant means it is equal to its Poisson bracket with h plus del I by del t 0. If that quantity does not contain t because there is no t here, it means only Poisson bracket with Hamiltonian. So it is a constant means Poisson bracket Hamiltonian 0. Taking Hamiltonian is given. Taking Poisson bracket with Hamiltonian, we found the value of A and B. The problem. Similarly, here problem it is Hamiltonian given for a simple pendulum. We have to find dl by dt. Hamiltonian given. You can also calculate the Lagrangian. We know Lagrangian Pj Qj dot minus L is equal to H. Obviously, H is equal to Pj Qj dot minus L. So what is L? L is equal to Pj Qj dot minus H. If you take L to left hand side and S to right hand side, so Hamiltonian given means you can also calculate Pj is P theta, Qj dot if you calculate it will be P theta by 2 ml square given. So from this you can calculate the dl by dt means if L does not contain T, it is only Poisson bracket of L with H. Okay. You can calculate this type of problem. Problems are here. Then another bracket is Lagrange bracket. For Lagrange bracket, formula is just reverse. Formula is Lagrange bracket with respect to Qp is equal to del Qi by del U into del Pi by del V minus del Pi by del U into del Qi by del V. Okay. Reverse of Poisson bracket. There are Q U by Qi or Qi by U. Okay. The fundamental Lagrange bracket also if same quantity 0, Qj Pj is equal to delta Ij. Also a transformation is canonical if its Lagrange bracket is 1. So you can also check if Lagrange bracket is 1, you can say it is canonical transformation. Okay? So from definition you see it looks Lagrange bracket is inverse of Poisson bracket. So if you take its product Lagrange bracket into Poisson bracket equal delta Ij. Okay. Okay. So its product is 1. Delta Ij means if I is equal to j, it will be 1. Okay. So you can check it given its proof. Generally, long question is not actual examination. So, but remember this relation. It is very important when you use. This derivation is given here. You can see. These are some problems. If Poisson bracket x p is minus 1, then find Poisson bracket x square plus p, p. Okay. X square p means x into x. So x into xp plus x into xpx plus p into p. X square plus p into p. X into xp. Actually, it is x. Oh, there is a term x square p plus p. If t x square p plus p plus p. Okay. That x square p is equal has two terms. Plus p plus p. P plus p actually 0. No meaning. So x into x plus p into x. Xp is minus 1, so minus 2x. Okay. These are the two problems. Something else. Okay. These are very important Poisson bracket, canonical transform, Hamilton's principle. Is it clear?
Yes, sir.
Hello?
Yes, sir.
Uh, so there is another thing is periodic motion in phase space, which is written motion in phase space. Phase space means QP space. Actually, periodic means it has a time period. After regular interval of time, it is change its position. Whether it is just like your sine wave, cos wave, or it is a motion, this type of repeating motion, circular motion, elliptical motion, or this type of motion, hyperbolic motion. Here, regular interval of time it changes. Right? It can come back to its original position. Here in sine wave case also 0 to 2 pi, then it is repeat 0 to 2 pi, 0 to 2 pi repeat. Uh, and so but there are two cases. One is so periodic motion can be defined in two ways. One is liberating system, another is rotation. Liberation and rotation. In the phase space, all such periodic system they not retrace their path with which retrace their phase space are called liberating system, which are not they are called rotation. All paths are not closed, but retracing like wave. which retrace their path, they call liberation. Liberation means your closed path or this type of path. But the wave path is no represent rotation. Rotation means if you rotate 2 pi to more, it will be again come back to its original position. Okay. There are two phases, liberation and rotation, all written there about periodic motions. This given picture, see, this is one is liberation and one is rotation. In liberation, is by rotation wave-like case. Angle, here angle is the variable. Uh, so we can check phase space diagram. Actually, there is a phase space diagram case. It is not important here. Which can be calculated from equilibrium case. We know for equilibrium, total force acting on this 0. But for conservative system, force is equal to minus del V by del X. So if its system is in equilibrium, its V is del V by del F0 means del V by del X0. With derivative 0 means it is either a stationary value, constant, maximum or minimum. For maximum, when V is maximum, in this case, we call it is a unstable equilibrium. Slightly disturbed it fell down. It cannot again came back to original position. But if it is V is minimum, then it executes simple harmonic motion about its equilibrium point. We call it stable equilibrium. So mathematically, how you know unstable stable is from second derivative. If second derivative greater than 0, we know V is minimum. Minimum means stable. If minimum always represents stable, you know, minimum energy is stable. And V, when V is maximum, then del square V by del X less than 0, we call it unstable. So you can calculate a stable unstable equilibrium from its second derivative of what V. Potential is given, we take its derivative equal to 0 and find the equilibrium point. And equilibrium point derivative 0. Then first take second derivative to check whether stable or unstable equilibrium. Okay. There are some questions. If potential is given, calculate its equilibrium point. For equilibrium point, del V by del X 0, del V by del X 2x minus 2b, equating it, you can find x value with this. Then you can check x is stable or unstable, checking second derivative. Second derivative this quantity, if it is greater than 0, then potential is minimum and it is stable equilibrium. Okay. In phase space, stable equilibrium point is act as an origin and unstable equilibrium point act as saddle point means interacting point where do one interact. So phase space, if you calculate a point is stable equilibrium point, and if you do diagram stable equilibrium point always with the origin. This point is stable equilibrium. Unstable point there actually intersection in the intersection is a saddle point where one breaks to other. Bifurcation. One breaks. We divide into two parts. This is the case for phase space diagram. Only if you remember this, you can tell what the diagram should be. Okay. Suppose here, for example, simple harmonic oscillator. Potential is half kx square. Right. You take its derivative kx. If k for okay. So x is equal to 0 is the equilibrium point. Kx is equal to 0 means x is equal to 0 is the equilibrium point. Then check its second derivative. Del square v by del x square means its derivative will be k constant. Was it if it is k is greater than 0, then only k greater than 0. So it means this potential minimum. Minimum is always act as origin. So if you draw the diagram of simple harmonic oscillator, x0 is the origin, is the diagram. Origin means there making center there is a circle. Okay. From potential you can know here also if there are simple harmonic oscillator 1 point, if you change the energy then you will get the similar type of shape. Number of shape refers to each energy. Again, particle motion between walls of a container involving to and fro motion. So you found its motion it going to this side and back to this side motion, but when it moving its direction is opposite, that means momentum is opposite. So its diagram, phase space diagram is like this. It what is the constant moving with constant energy, but when get in back motion, its energy or momentum you can say in opposite direction. There are other problems also. Potentials are given. From this you can calculate, and some problems given shape of the diagram. Okay. Okay. These are the shape of diagram from this potential. A potential is given. You take its derivative. From derivative you find 0 and plus minus 1 are equilibrium point. For okay, for 0 it is unstable negative and plus minus 1 are stable. So unstable means in 0 there is a bifurcation, but from 1 to its origin. Okay. So its diagram is look like here actually. This here reverse case plus minus 1 is unstable, 0 is stable. That potential looks like. Okay, this is the picture. Now from potential you can draw the phase space diagram. These are very complicated one. They not act, but simple things may be act in your question, like these two cases. For harmonic oscillator, phase space diagram is a ellipse because energy of kinetic energy plus potential energy. And kinetic energy is p square by 2m. Potential energy is half k q square or half k x square. So it is phase space means QP. It is a equation of ellipse. X square y square plus y square b square 1 x q square also ellipse. Also from here you can say it is ellipse. A greater than 0 from potential is its ellipse. Okay. Is it clear? Hello? Hello? Am I audible? Hello? 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 Am I audible? Hello? Hello? Am I audible? Hello? Hello? Am I audible?
Sir,
Huh. So this is all about part one. Mm, okay. And then I think I will stop here. Okay, I will send all the materials. Tomorrow you will study it, and if in doubt, then ask me. Hello?
yes,
Okay.
sir.
Okay. So, okay, thank you.